Content in this presentation is covered on pages 239 through 254 of your textbook, and it's meant to help you achieve learning objective number 40, which is to list 4 types of local winds and describe their formation. Be sure to skim these pages before watching the video and read the chapter carefully before attempting the online quizzes. On a slightly larger scale than mesocyclones like tornadoes, local wind systems, which include sea and land breezes and mountain and valley breezes, rely on thermal circulation to generate flow over spatial scales of tens to hundreds of kilometers. Thermal circulation systems begin as relatively cool air sinks in response to a daily lowering of surface temperature after the daily high has been reached. Similarly, after the daily low temperature, when the ground temperature begins to increase, warming air starts to rise. In some places, a region of warming air temperature can be found immediately adjacent to a region of cooling air. In these cases, the sinking air may generate a regional surface low pressure region, while the rising air generates a regional surface high pressure region. As air at the surface moves from high to low pressure, air aloft may be flowing in the opposite direction. An example of this type of thermal circulation is the sea and land breeze, in which a daily cycle of warming and cooling brings cool wind onshore during summer afternoons and pushes cool air back over the ocean during the nighttime. Remembering that we label the wind according to the direction it is flowing from, you can see that the sea breeze is the cool onshore flow from over the ocean, and the land breeze is the warmer offshore flow from over the land. Because the land is a better conductor of heat than water is, its temperature increases much more quickly as solar radiation starts to heat the ground surface after sunrise. The ocean surface temperature increases much more slowly, leaving it relatively cool. As air molecules rush in toward land, they begin to accumulate, and by late afternoon, you'll see clouds form over the land. In many cases, the pressure becomes so low that these will develop into thunderstorms that begin to cool the hot ground surface. So notice that there are 8 gray lines that represent surfaces of equal pressure surface. Those are imaginary surfaces. They would appear as isobars on a weather map wherever they intersect the ground surface. In the drawing of the sea breeze, you can assume that the pressure gradient force is stronger, so the winds are a little bit faster. What causes the PGF to be stronger during the day is the dramatic difference in temperature. The temperature difference between the water and the ground surface is much greater during the day. The ground gets really hot while the water in the ocean absorbs heat. The ground gets really hot while the water in the ocean absorbs heat much more slowly. At nighttime, the water will give up its heat more slowly too. So not only does it warm more slowly, but it cools off more slowly. So it's likely to stay about the same temperature, roughly, throughout the night compared to the rapid cooling that happens over the beach. Florida is known as Thunderstorm Alley because it has converging sea breezes from the Gulf of Mexico and from the Atlantic Ocean. In the afternoon, the convergence of the 2 local wind systems causes substantial uplift that enhances thunderstorm development and rainfall. However, when westerly surface winds dominate and a ridge of high pressure forms over the area, thunderstorm activity diminishes and dry conditions prevail. But in this illustration, you can see the effect of the approaching winds from the two different oceans. A daily wind similar to land and sea breezes occurs in mountainous regions. During the day, air along mountain slopes is heated more intensely than air at the same elevation over the valley floor. This warmer air glides up the mountain slope and generates a valley breeze. Valley breezes can also be identified by the cumulus clouds that develop over adjacent mountain peaks and may account for late afternoon thunder showers that occur on warm summer days. After sunset, the pattern reverses. Rapid heat loss along the mountain slopes cools the air, which drains into the valley and causes a mountain breeze. Similar cool air drainage can occur in hilly regions with modest slopes. The result is that the coldest pockets of air are usually found in the lowest spots. Like many other winds, mountain and valley breezes vary by season. Valley breezes are most common during warm seasons when solar heating is most intense, whereas mountain breezes tend to occur more frequently during cold seasons. Warm, dry winds, called Chinooks, sometimes move over the slopes of mountains in the United States. Similar winds in the Alps are called fanes. Such winds are usually created when a strong pressure gradient develops in a mountainous region. As the air descends the leeward slopes of the mountains, it's heated adiabatically by compression because condensation may have occurred as the air ascended the windward side, releasing the latent heat. The air descending the leeward side will be warmer and drier than at a similar elevation on the windward side. Chinooks commonly flow down the east slopes of the Colorado Rockies in the winter and the spring, when the affected area may be experiencing sub-freezing temperatures. So those dry, warm winds often bring about drastic changes. Within minutes of a Chinook's arrival, the temperature may climb 20 degrees C. These winds can rapidly melt snow cover, which explains why they are named Chinook, which is a Native American word for snow eater. Chinook winds have been known to melt more than a foot of snow in a single day. A Chinook that moved through Granville, North Dakota on February 21st in 1918 caused the temperature to rise from minus 33 Fahrenheit to 50 degrees Fahrenheit, an increase of 83 degrees Fahrenheit. Chinooks are sometimes viewed as beneficial to ranchers east of the Rockies because they keep the grasslands clear of snow during much of the winter. However, that benefit is offset by the loss of moisture that the snow would leave to the land if it remained until the spring melt. Another Chinook-like wind that occurs in the United States is the Santa Ana. Occurring in Southern California, the hot, dry Santa Ana winds greatly increase the threat of fire in an already dry area. Surface weather maps like this one showing the Santa Ana conditions in January show you that a maximum temperature for the particular day are given in Fahrenheit, and they can, degrees Fahrenheit, they might be 54 over northeastern Utah, and pushing wind over through the Santa Ana Valley at 88 degrees. So temperatures in the upper 80s, while everywhere else the temperature readings are much lower. Santa Ana winds are driven by strong high pressure systems with subsiding air that tends to develop in the fall over the Great Basin. The clockwise flow from the anticyclone directs desert air from Arizona and Nevada westward to the Pacific. The wind gains speed as it's funneled through the canyons of the coast ranges, in particular the Santa Ana Canyon. Adiabatic heating of that warm, dry air further accentuates the already dry conditions, and vegetation seared by the summer heat is dried even further by those hot winds. Although Santa Ana winds occur every year, they were particularly hazardous in the fall of 2003 and to a lesser extent in 2007, but again in more recent years. When there were hundreds of thousands of acres scorched by these fires. In late October 2003, Santa Ana's winds began blowing toward the coast of Southern California at speeds sometimes greater than 60 miles an hour. Much of the area is covered by brush known as chaparral and related shrubs. And it doesn't take much. One careless camper, motorist, or a lightning strike or an arsonist starts a big fire. Soon a number of the small fires occur in parts of Los Angeles, San Bernardino, Riverside, San Diego counties, and several quickly developed into wildfires that moved almost as fast as the winds themselves, sweeping through the canyons. Within a few days, more than 13,000 firefighters were on fire lines extending from north of Los Angeles to the Mexican border. And nearly 2 months later, when all the fires were officially extinguished, more than 742,000 acres had been scorched, more than 3,000 homes destroyed, and 26 people were killed. In the winter, areas adjacent to highlands may experience katabatic winds, also known as fall winds. These are local winds that originate when cold, dense air over highland areas, like the ice sheets of Greenland and Antarctica, begin to move. Under the influence of gravity, the cold air cascades over the rim of a highland like a waterfall. Although the air is heated adiabatically, the initial temperatures are so low that the wind arrives in the lowlands still colder and more dense than the air it's displacing. As that air descends, it occasionally is channeled into narrow valleys where it acquires velocities capable of some pretty intense destruction. A few of the better known katabatic winds have local names. The most famous is the Mistral, which blows from the French Alps across the Mediterranean Sea. Exceptionally hot, dry air also cascades out of North Africa and the Saharan desert, influencing in a monsoonal manner, influencing other parts of the Mediterranean. We'll talk more about this in future presentations.